Okay, we're getting into section 7.5, in which we're going to introduce a whole bunch of new identities and work with them. They're called the sum and difference formulas. Okay, specifically, we want to learn how to use them. The objectives are pretty straightforward. What are the sum and difference formulas? Can we use them? Yes. Okay, so here are some formulas for the cosine of either a sum of two angles or the difference of two angles. The first one is called the sum formula for cosine. The second is called the difference formula. I think it's pretty apparent. I have a sum or a difference. Don't worry about memorizing these formulas, okay? You can look them up. You're given a formula sheet to refer to on exams, so you don't have to memorize formulas. But just note that the cosine formula says cosine cosine minus sine sine, and this minus corresponds to that being a plus. And if I switch this to a minus, this just switches to a plus. But it's still a cosine and a sine and a sine. What good do these formulas do us? So we have explicit knowledge of like what's the sine of pi over 6, pi over 4, pi over 3, and that's about it in the first quadrant. With these formulas, however, we can start to get nice exact knowledge about a whole slew of other angles. For example, can we find the cosine of 105 degrees? The way we do it, we find two angles that we know how to deal with, whose sum or difference is 105 degrees. So 60 plus 45 is 105. And I know the sine and cosine of both 45 degrees and 60 degrees. So this formula from the previous slide says, instead of cosine of 105, call it cosine of 45 plus 60 degrees. The sum formula for cosine says cosine of the first times cosine of the second minus sine of the first times, this is supposed to be a sine, of the second. And I know all of these values, okay? The cosine of 45 degrees is root 2 over 2. The cosine of 60 degrees is a half. The sine of 45 degrees is root 2 over 2. And the sine of 60 degrees is root 3 over 2. We've got a common denominator of 4 that we factor out, leaving behind root 2 minus root 6. Please observe root 2 minus root 6 is definitely not the square root of 4. It's just whatever it is, it's a negative number. But note that 105 degrees is in the second quadrant, where the x-coordinate is negative, so we expect the cosine to be negative. So here we have it. This is the exact value of cosine of 105 degrees, 1/4 times the square root of 2 minus the square root of 6. So how about cosine of 5 pi over 12? Can you come up with two angles that you know how to take the sine and cosine of that either add or subtract to give you 5 pi over 12? Well, we've got more than one possible way to do it, but I think the most straightforward is 2 pi over 12 and 3 pi over 12. And you might think, why on earth are 2 pi over 12 and 3 pi over 12 convenient? Because they're pi over 6 and pi over 4, and we know how to deal with those. Then the sum formula for cosine says cosine of the first, cosine of the second, minus sine of the first, sine of the second, all of which we know. And that simplifies to 1/4 times the square root of 6 minus the square root of 2. Again, we now have an exact value. This is not a calculator approximation. This is flat out exactly what the result is. This is the cosine of 5 pi over 12. Here are some further identities, and these aren't really new, okay? We kind of observed back when we were doing graphs that the graph of sine and the graph of cosine are basically just horizontally translated versions of one another, and that's what these say. Start with the cosine curve, do a horizontal reflection, and then shift right by pi over 2 by 1 quadrant, and you will have the sine curve. Take the sine curve, do a horizontal reflection, and shift left, sorry, by pi over 2, and you'll have the cosine curve. Okay. So, the nice thing about these formulas is that they look more or less the same. Okay? Either the cosine or sine of pi over 2 minus theta is the sine or cosine of theta. So it's fundamentally the same sort of formula for both of them. But it allows you to replace a cosine with a sine or a sine with a cosine. In some examples, some applications, for example, you might have a trig function and the assumption is you're going to use a cosine. But someone else may say, I need a sine. I only programmed my application to accept inputs of a sine function. But I have a cosine function, and you say, okay, fine. If I have this cosine function, I can transform it into a sine function by changing the argument. There's not really a difference between sine and cosine functions. They have the same behavior, they're just shifts and reflections of one another. Okay, we also get this sum and difference formula for sine. They're different formulas from the cosine one. For example, in the sine formula, each term has a sine times a cosine. Whereas in the cosine formula, you either had cosine cosine or sine sine. Here they get mixed up. Also, a plus here gives me a plus here, and a minus here gives me a minus here. That's different. And you might be saying, oh my gosh, how am I ever going to remember that? You don't have to. Okay? Again, don't worry about memorizing formulas. If you happen to memorize it because you do a lot of practice problems, that's great. But you don't have to memorize it. You will be given a formula sheet because math is not about memorizing stuff. Okay, so let's use these formulas to get sine of other angles. So for example, can you get the exact value of the sine of pi over 12? So can you think of two angles whose sum or difference is pi over 12, and you know the sine and cosine of both? Yep, pi over 4 minus pi over 6. 3 pi over 12 minus 2 pi over 12. That gives you the sine of pi over 12. We use the difference formula now. Sine of first, cosine of second, minus cosine of first, sine of second. And you just have to check. Back on the previous slide, it would have said the following. It would have said the sine of A minus B, I think it used alpha and beta, whatever, is sine A cosine B minus cosine A sine B. So just observe one angle minus another, sine of the first angle cosine of the second, sine of the first angle minus, times cosine of the second, minus, and then you switch the two. So just check that you get everything in the right order. But the good news is we do know the value of sine pi over 4, etc., etc. Root 2 over 2, root 3 over 2, root 2 over 2, and 1/2. And there we have it, 1/4 times root 6 minus root 2, which was actually the cosine of 5 pi over 12 from earlier. But hey, we also just saw something that the cosine of pi over 2 minus theta is equal to the sine of theta. Well, heck, if theta is pi over 12, not 16, 12, we get exactly the sine of pi over 12 is the cosine of 5 pi over 12. So we already knew that anyway. Okay, how about this? This is kind of going the other way. I don't know what the sine of 75 degrees or the cosine of 15 degrees is. But can I find an exact value for this? It's a little, contrived, but yes, it matches the sum formula for sine. So instead of sine 75 cos 15 plus cos 75 sine 15, you would say that's just the sine of 90 degrees, which is 1. So even though I don't know an exact value for each of these things individually, I am quite certain that the end result is just going to be 1. And that's just using the sum formula for sine in the opposite direction that we had used it in the earlier example. So we have introduced sum and difference formulas for sine and cosine. That's what we introduced here. If you come back in the next video, we're just going to keep working through problems, and we're going to introduce some more stuff in this section. Okay, but to begin with, we're just going to come back and do more examples.